Hi, welcome back to Mrs. O'Graham's Maths. Today we are looking at the worked solutions for the D&D Resources. We're in the complex numbers booklet. That is standard number 91577, and we're doing practice external assessment number 5. So again, a thank you to D&D Resources for allowing me to share their materials in this way and provide these worked solutions for you. I have put a link to their resources in the video description, so you can go and order physical copies of this if you don't have them already. Are a really excellent resource, and I highly recommend getting the physical copies so you can actually practice writing these out like they are for the real exams. Okay, so for question 1, we are going to rationalize the denominator here. So we have 4 minus root 2 on the top, 2 root 2 minus 1. Now we need to times it by the negative third part of the denominator. That's how I go about these things. So the bit that we're trying to get rid of is the third on the bottom, so make that bit a negative, like this. It's similar to what we do when we've got complex numbers on the bottom. Just going to make that a little bigger so my writing is not going so horrible. Okay, now let's multiply across the top. We have minus 8 root 2 times by, so these two things times together are going to be root 2 times by root 2 gives us 2, and then times by the 2 will be a 4. The minuses cancel, so we've got a plus 4. Then if we multiply through by the minus 1, we've got minus 4 and a plus root 2. On the bottom, these two times together, we've got the root 2 times the root 2 makes the 2. We've got the 2's on the outside times together make a 4. So multiplying them together gives us an 8. And then the positive one of this and the negative one of that will cancel each other out, and we have minus 1 times minus 1, which is a plus 1. So we have minus 8 root 2 plus a root 2 is minus 7 root 2. The 4 minus 4 cancels on the top. We have minus 8 plus 1 is minus 7. The minus 7's cancel, so that's equal to root 2. For part B, we have 3 plus I divided by V is equal to 1 plus I. So V would be equal to 3 plus I divided by 1 plus I, which we can do on the calculator. So let's pop that in. 3 plus, let's get our complex stuff up. Here we go. 3 plus I divided by 1 plus I is equal to 2 minus I. So then UV is 3 plus I multiplied by 2 minus I. So let's times that together. And we've got 7 minus I. Now, there's a couple of ways you can go about doing part C. You could do long division. I have found that most people don't really like long division when I teach that, so I do an alternative called algebraic juggling. You may have seen it, but called something else. There's videos on this on my channel if you want to do any kind of algebraic division. There's both of those methods are available on my channel if you want to go and look them up. So I'm going to go through algebraic juggling, which is to say that we've got this expression here, and we're dividing it by x minus 2. So what we do to start with is pop the x minus 2 up on the top and see what do we need if we are trying to make the first term here. So if I'm making 3x cubed by multiplying by x minus 2, I need a 3x squared on the outside. Now that would give me the 3x cubed if I multiply that out. It would also give me a minus 6x squared. So we compare this term here to the next thing that came along just there. Instead of it being minus 6, it's a minus 5. So we need to add an x squared back on so that it would be equivalent. The other way to think about it is that this would give me a negative x 6x squared, so I need to add that 6x squared back on, then write in the rest of what comes after on the expression that we had. Let me just finish doing that. And then these two together simplify that. So minus a plus 6x squared minus a 5x squared is going to be a plus x squared. So from this point onwards, I'll be doing it all in one step like this, but I'll just explain that fully for the first one. Okay, now what that means is we can take out the 3x squared x minus 2 over x minus 2 and then deal with the rest of this as a separate fraction. And we do that because those two things will cancel, so we're just left with the 3x squared. Okay, so we've got 3x squared, and then if we do the same thing with the other part, we've got x minus 2. To make the x squared term at the beginning here, we will need to multiply by an x on the outside. That x squared, if we expand that bracket now, we do x times x gives us the x squared. It also gives us the minus 2x, which is what we wanted just here. So this one doesn't need any adjusting, and we're just left with the plus 4 at the end. So then this becomes 3x squared. This portion of the fraction can be pulled out to be just x, because the x minus 2's would cancel, and then we're left with plus 4 over x minus 2. Now compare that to what we had in the question here, and we can write down the values that a is 3, b is 1, and c is 4. For part D, we've got this complex number that's going to need a bit of tidying up, but we know that it lies on the line x equals y. If that's true, then the real portion will be equal to the imaginary portion, because it's on that 45-degree line. So let's take the 2p plus I over 2 minus I and rationalize the denominator first, so that we can try to pick out the real and imaginary parts of this. Okay, so multiplying across by 2, we'll get 4p plus 2i. Then timesing by I, we will have 2pi plus I squared. On the bottom, we get 4 minus I squared. So now let's simplify that. The I squareds obviously become minus 1, so the real part on the top is 4p minus 1. The imaginary is 2 plus 2pi, and then the I squared on the bottom is minus 1, times by the minus becomes a plus, so that'll be over 5. Now if the real is equal to the imaginary, that gives us the real part on our expression just here for the complex number is the 4p minus 1 over 5, and the imaginary part is 2 plus 2p over 5. So those 5's cancel, and we end up with the numerators being equal to each other. Bring the p to the left-hand side. We've got 2p, take that 1 over, we've got 3, so p is equal to 3 over 2. Okay, we're doing locus for part E, and as is usual for locus questions, we're going to start by writing z is equal to x plus iy and pop it into the thing that we've got here. All right, so modulus means that we will do the square root of the real part squared. So the real part on this, if we pop that in as x minus iy for z, we have x minus 3 is the real part. The imaginary part is y plus 2, and then that gets square rooted. On the right, we've got, again, if we've got x plus iy in for z, the real part here will be x minus 6, that gets squared, and the imaginary part is y plus 1. So the square roots cancel each other out. We need to expand those brackets inside of them. So we go ahead and do that. It's going to be 4y plus 4. And we've got x squared plus, oh no, minus 12x plus 36, y squared plus 2y plus 1. Let's start cancelling off things. So x squared and x squared, y squared with y squared. Let's see what we're left with now. Okay, so we've got, if we bring all the x's over to the right, in fact, I'm going to bring everything over to the right and see what we've got. So 12x comes over and adds on to the minus 6x, so we've got a 6x. The y's, we'll have a 2y. Then we've got 9 plus 4. We're going to take off the 36 and we'll take off a 1. It's equal to minus 24. Now we can divide everything by 2. And y equals minus 3x plus 12. So that's the equation of the line that matches this locus. Back to what the question was asking for is that we've got a complex number that sits on that line. We need to work out the value of a if that's true. So if it matches this line, then the x and y coordinates go in as being this a and a from the complex number. So the y coordinate being the imaginary part is the a, and the x coordinate is the real part. It's that a there. So minus 3a plus 12. So then we've got 4a equals 12. So a equals 3. For question 2, we are solving this quadratic. So z is equal to minus b, which is 6, plus or minus the square root of b squared minus 4 times a, which is 3, times c, which is 7, all over 2a, which is going to be 6. Okay, so the 6 divided by 6 gives us 1, plus or minus. Now we've got 36, take away 4 times 3 times 7 is negative 48 over 6. Now just off to the side, I'm going to sort out the negative 48. So this is negative minus 1 times by negative, square root of minus 1 times by the square root of 48. Square root of minus 1 is I. Now 48, let's try and take out a factor that is a square number. So you can do 48 divided by 16. That gives us 3. So that's the square root of 16 times 3. So the square root of 16 is 4. So we'll have 4 root 3, and then it gets times by the I. So back over to what we were doing. This is now 1 plus or minus 4 root 3i over 6. Now the 4 over 6 can cancel. So that's going to be 1 plus or minus 2/3 root 3i. And I've deliberately written the 2/3 out in the front because the question wanted it in this format here, so it's really clear what part is B and what part is C. Okay, part B, we've got u and v are complex numbers as shown here. Show that uv will always be real, so we need to do uv. So a plus ai times by b minus bi, and then expand it. So we get ab minus abi plus abi minus abi squared. So the two abis cancel because it's a minus and a plus. We're left with ab. The I squared becomes minus 1, so it's plus ab. So that is 2ab, which has no imaginary parts, therefore it is real. Okay, so let's try and sort out this equation. Solving for x in terms of p means we want x equals something. So let's aim for that. Squaring both sides to get rid of the square root first. We've got p squared x plus 2. Don't forget to square the bit that's outside of the square root sign as well. On the right, we'll have 9 times x. So we now get squared x plus 2p squared minus 9x equals 0. That helps me to factorize out an x in this way, so we can say p squared minus 9 plus 2p squared is 0. So x p squared minus 9 is equal to minus 2p squared, and x is minus 2p squared over p squared minus 9. And there's one small consideration to make at the end, which I don't know for certain if you would actually need to do this on this question, as it hasn't specified it in the question, but just in case, you need to consider what p could be. So p can't be equal to plus or minus 3 in this case, because if you put that into there, it would make your denominator 0, and you can't divide by 0. So it's worth noting that the full solution does include this bit, that p can't be equal to plus or minus 3. Okay, for part D, we are doing operations in, well, actually it's mixed up polar form and rectangular form. I'm going to start with the polar stuff that's on the top. So in polar form, if you are multiplying two things together like we have here, just on the top bit there, sorry, then what happens is the modulus gets multiplied together. So we've got the k squared, but the argument gets added. So we've got a quarter plus a half of pi there. Oops, let me just pop that in again. There we go. Which is 3/4 of pi. So we've got 3 pi by 4 on the top. Now divided by k cubed I. To be able to do a division, we need to either have it all in rectangular or all in polar form. I'm going to do it in polar. I find that's going to be easier. So if we think about where k cubed I is on the Argand diagram, it's up here. So k cubed I. It will have an argument of 90 degrees, or pi by 2, and a length of k cubed. So this will be k cubed cis of pi by 2. Now if we are dividing, then the modulus gets divided. So the k squared divided by k cubed is k to the minus 1. And the argument gets subtracted. So we've got 3/4 pi minus a half is going to get us back to a quarter of pi by 4. Now we want our answer in rectangular form. So again, thinking about the Argand diagram, where is that going to be? Well, pi by 4 is just here. It's on that 45-degree line, so the real and imaginary parts will be the same. Think of it as a little triangle with equal sides there, and an angle of pi by 4. The modulus is k to the minus 1, which is 1 over k. Then using Pythagoras, those two sides are the same. A squared plus a squared has to equal 1 over k squared for Pythagoras. So 2a squared equals 1 over k squared. A squared will be equal to 1 over 2k squared. So a is the square root of that. It would be 1 over the square root of 2 times k. Because of where we can see where it is on the Argand diagram, we know it'll be the positive roots for that. So in rectangular form, this equals 1 over 2 root 2k for the x direction, plus the imaginary part is a in the imaginary direction, so it'd be 1 over root 2ki. Part E, we're told that we want the values of k for which we have real solutions. Now for real solutions, we want to find the discriminant b squared minus 4ac and make sure that it's positive. The tricky part is we don't have this as an ordinary looking quadratic, so we need to do some manipulating to make that into the form where we can pick out b squared minus 4ac. Okay. Let's start by getting rid of what we have on the bottom of these fractions by multiplying everything through by 6. So if we do that first bit times by 6, we'll end up with 2 times root kx plus 5. The x over 2, if we times that by 6, we'll have 3x, and then we have 6 over here. Now I want to be able to square things to get rid of that square root. So let's start by putting all of the rest of the terms in one spot on the other side, like this. Actually, let's write the 3x first. Just looks a little better. Now we're going to square both sides. So we end up with 4kx minus 5 on the left. Don't forget to square the 2 as well. This will be 3x plus 6 squared, which is the same as timesing by 3x plus 6. So make sure you don't miss the middle terms here. So we'll get 9x squared. 6 times 3x is 18, and that will happen twice. So we have 36x, and then 6 squared is 36. This is 4kx minus 20. And the final step, I'm going to take this piece and take it over to the right hand side so that we have a more normal looking quadratic. So we'll have 9x squared plus 36x take off 4kx plus 36 plus 20 will be plus 56. And I've just spotted an error that I've made all the way through from this bit just here. That should have been a plus. So that's a plus, and that makes it 36 take off the 20. So that'll be a plus 16 in here. Apologies for that. Okay, so 36 minus 4k in the x's. If we just take that out as a factor so that we can easily pick out the b portion of this. So now b squared minus 4ac will be 36 minus 4k squared minus 4 times 9 times 16. So expanding this bracket, 36 squared is 1296. The 4 times the 36 will happen twice over, so that'll be minus 288k, and then plus 16k squared. 4 times 9 times 16 is minus 576. So we end up with 1296 take off the 576 is 720. So we'll get 16k squared minus 288k plus 720. And we want to make it real, remember? So if we go up to the top of our question here, we're making that greater than 0. Now that looks to me like everything will divide through by 16, so I'm just going to check that. Yeah, we've got a 45 on the end. 288 divided by 16 works as well. So this will be k squared minus 18k plus 45 is greater than 0. We can pop that into our equation solver to get where this, or actually it might, I'm going to go for the graphing option this time around, just so we can see the picture. So let's pop that in, but we will use x's in place of k, like this. Okay, and let me just fix my view so that we can see everything. It didn't quite work. Let me just do a bit more adjusting. Try that one. Okay, so now we can see the picture of it, and we can see that this goes below 0 here. We want where it's above 0. So we want everything to the left of this intersection point and everything to the right of this intersection point. So we'll find the intersection points, or the roots for the x-axis. So the first one is at 3. So k has to be less than or equal to 3 actually. It can be equal to 0 and that would still count as real. And then the next root, move it along, we'll find that k has to be more than or equal to 15. Okay, now on with question 3. For A, we need to find the value of this if Z is just here, and then put it onto the Argand diagram. So Z equals minus 2i. It's got no real component. If we do I squared Z squared, that will be minus 2i squared times I squared. So that's 4i squared times I squared. I squared is minus 1. And so we end up with it being equal to 4. And now let's plot that onto the Argand diagram. So that's on the real component just here, no imaginary parts. So this here is I squared Z squared. For part 2, we've got Z is equal to U squared over V. Well, U squared, let's pop that into the calculator. We got minus 2 plus 2i, and then square that, gives us minus 8i over V, which is in polar form, and we're going to end up with it being in polar form. So I'm going to leave that as it is for now. So that'll be 4 cis pi by 3. Then minus 8 on the Argand diagram will be just here, minus 8i, apologies. It's going to have a length of 8, so it'll be 8 cis, and then the angle here is a negative pi by 2 over 4 cis pi by 3. So if we do 8 divided by 4 for the modulus, we've got 2. When we are dividing in polar form, we subtract the argument, so we've got a negative half of a pi, take away a third of a pi. That's going to be negative 5 pi by 6. For part C, we're told that one of the roots is 2 minus I. Now, if you're given a complex root, you can straight away write down that its conjugate is also a root. So 2 plus I is also a root. We need to work out the A and B in there. Now, if it's a root, it means we can put it into the equation and it will make it true. So 3 times 2 minus I cubed plus A times 2 minus I squared, B times 2 minus I minus 5 will equal 0. So let's go through and work out what that would be. 6 minus 33i from this first bit. (3a minus 4ai here). 2b minus bi minus 5 equals 0. Now let's take a look at the real portions in there. We have the real parts, there's anything without an I on it. We have 6 plus 3a plus 2b minus 5 equals 0. So 3a plus 2b is equal to minus 1. Then the imaginary parts. So we can get these bits that have the i's with them, and there's also a 0 I on the right. So we got minus 33 minus 4a minus b minus, is equal to 0. Or minus 4a minus b is equal to 33. Now we go to equation solver. We are doing a polynomial. No, we're not. We're doing simultaneous with two unknowns. So we've got, just check that you're putting this into the format the calculator's expecting. X plus y then is equal to constant. So we've got 3, 2, minus 1, and minus 4, and minus 1 is equal to 33, and then solve. So we have now got that a is equal to minus 13 and b is equal to 19. Then we can go back and use equation solver again to get the third root. So we're doing equation solver. on 3x to the power of 3 plus, or actually it's minus 13 for the a. So all I'm doing now is putting this equation in, but we're subbing in the values of a and b that we know. So that'll be of x squared plus 19x minus 5 is equal to 0. So we've entered that. Now, just because I want for completeness to show all of the solutions to check I'm doing this right, I'm changing my mode to be complex solver. Now let's solve that, and I've put something in wrong. Let's just check that. I often mix up the types of negatives that I enter into here. It needed to be this subtraction rather than the negative that's just next to the execute. Right, let's enter that. Solver gives us that x is a third. So the final solution is that z3 is equal to a third. Okay, let's go with w is 3 over z and subbing in the z. Now let's do the complex conjugate so we can rationalize that denominator a little bit and be able to find the argument. So if we multiply across here, we get 3 root 3 plus 3i. And 3 root 3 times root 3 on the bottom is 3 minus I squared. So that's equal to 3 root 3 plus 3i over 4. Now we need to find the argument. We're in the positive quadrant of our Argand diagram here. Think about the triangle that we'd make with w. In the x direction, we've got 3 root 3 over 4. In the y direction, or the imaginary direction, we have 3/4. So the argument of w will be this bit just here, that angle. Now looking at that triangle, we've been told to give the exact value, so we can't just pop it straight into doing trig. That won't give us an exact value. So the clue here is to look on your formula sheet. If you're being asked to give an exact value for this particular type of triangle, find what triangle that's similar to. So we could divide both of those sides through by 3/4. They've got a common factor of 3/4, and then it becomes a 1 and a root 3 here, and it would have the same argument of theta. Now, if you look on your formula sheet, you have a special triangle like that. And the hypotenuse of it is to do root 3 squared, which is 3, 1 squared is 1, add them together is 4, and we've got square root that length is 2, so that might help you find that triangle even more easily, where you've got the 1, the root 3, and the 2. That makes this theta argument the triangle that shows you that that theta is pi by 6. I'll just quickly pop over and show you the bit that I'm talking about on the formula sheet. It's this triangle here, where you've got a 1, a root 3, and a 2, and the angle that's positioned in the places where those 1s, 2s, and root 3s match up with what we were looking at, or in other words, the angle that's opposite the 1 is pi by 6. For part E, we've got quite a bit going on here algebraically. We've got this complex number for z that we're going to need to tidy up before we can do much with it. We're told about its modulus and its argument, but we can't use them until we've got z in the form of x equals real plus imaginary part. So we're going to work on that first. I'm going to do this by putting it over a common denominator. So if we were to make that common denominator 4 minus 2i times 3 plus I, then the a part will be multiplied by the 3 plus I. We've taken away b part on the top, and because we've got the subtraction just there, and that needs to be times by 4 minus 2i. Now on the bottom we can do that on the calculator, so 4 minus 2i times by 3 plus I gives us 14 minus 2i. Then on the top here we've got 3a, ai, 4b, 2bi. Then we'll times that by the complex conjugate of the bottom to rationalize the denominator there. Okay, so 3 times 14 is going to give me 42a. Then 14ai. And we've got minus 56b plus 28bi. Then putting the 2i, multiplying that across, we'll have 6ai, 2ai squared. So that's going to become minus 2a. Then we have minus 8bi plus 4bi squared. And again, the I squared becomes minus all over 14 squared is 196. Oh, that should have been a minus 2i just there. Plus 2i. Then minus 2i times positive 2i will give me a minus 2i squared. The I squared, oh wait, no, it's a 4i squared. The I squared becomes minus 1, so that'll be a plus 4. Okay, let's collect up the terms. So the a's, we've got 42 minus 2 is 40a. The ai's, spotted a little mistake on this one. That should have been a plus because we were doing the positive ai times 14 there. So that will be a plus 20 ai. The b's, we've got a minus 56 and a minus 4, so we end up with minus 60b. And the bi's, we've got 28 minus 8, so that's a plus 20bi. And 196 plus 4 is 200. Now we can see there's a common factor there of 20. We can divide everything through by 20. I'm also going to get the real parts together and the imaginary parts together. So the real parts are the a's and the b's, and if we divide them through by 20, we have 2a minus 3b. The imaginary parts divided through by the 20, we have a plus b times the imaginary part, and 200 divided by 20 is 10. Okay, now we need to use the information we've got here. So with the argument being equal to pi by 4, that means that you are on your 45-degree line on the Argand diagram, like this. So the real and imaginary parts will be equal to each other. So we will have 2a minus 3b over 10 is equal to a plus b over 10, and the 10's cancel. So we just have 2a minus 3b equals a plus b. The other part is that the modulus is 2 root 2. So the modulus of z is the real part squared plus the imaginary part squared and then square rooted, and we're told that that equals 2 root 2. So we'll need to solve these simultaneously, and I think it's going to be easiest to do that by substitution. So on the left hand side, we can take the a's over to the left. We've got an a, and on the right, bring the b's over. We'll have that equal to 4b. So now we can substitute in 4b in place of a on this one that we've got on the right. Let me just carry on in another color here. Okay, so on what I'm going to do first of all is square both sides. So if I put in 2 root 2 and square that, that will give me an 8 is equal to, now 2a on the top there will be 4b times 2, so that'll be 8b minus 3b over 10 squared. And then if we put 4b in for a here and square that, we end up with 8b minus 3b is 5b over 10 all squared. And sorry, it's minus 5. No, it is 5b. And then this one will also be 5b over 10 squared. Well, 5 over 10 obviously cancels to a half, so that's b over 2. Okay, so now we have b squared over 4. So that's 2 lots of b squared over 4, or b squared over 2 is equal to 8. So b squared equals 16. B would be equal to plus or minus 4. Now, thinking about the context of this question, where we're told that we are in the positive quadrant because the argument is pi by 4, to keep that true, our b would be the positive version of that square root. So b is equal to 4. That would make a equal to 4 times 4. So a is 16.